Okay, let's wait for a few more minutes. Let's see if anyone joins or not. Yeah, so let me wait 1 or 2 minutes more. Let's see if anyone else joins or not. Then we will start. Uh-huh.
Semaphores, etc.
Yeah, yeah, I know. Have you gone through the slides?
Yeah, I was not able to understand.
Yeah, okay, so let me try. Okay, so okay, I understand like these topics are little difficult, but at the same time, with examples, you'll be able to understand what they are trying to do. Okay, so let's start. I don't think anyone else will join. So hello everyone, my name is Rajoy Mukherjee, and I'll be taking this online live session for NPTEL course on operating system fundamentals. I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So this week's course we will have a small recap, and then we will solve some questions. So let's begin. Okay, so previous week we have discussed what is the critical section problem, where uh, basically the idea is this. So you have a piece of code. Let's say it is like update bank statement. You saw what happened when two or more two two transactions happened concurrently. So the example was at one end, one task was trying to debit one task was trying to debit rupees 1,000. Let's say the bank balance was initially 10,000. One one transaction was deducting rupees 1,000 from your account. Another transaction was debiting uh, debiting 2,000 rupees from your account. What showed is that after the transaction, the amount could be either 9,000 or 8,000. But if these two transactions happened concurrently, uh, atomically, we came across this term called atomic, which means the one which means that this task has to be done one at a time. This is a critical task. So if so why we want an atomic transaction is because if this transaction happens consecutively, so the suppose let's say first T1 happens, T1's reads the balance, then T2 reads the balance, then T1 writes the balance, and T2 writes the balance. So the output at the end will be 8,000. Whereas if we are able to successfully do this transaction, it should be 10,000 minus 1,000 minus 2,000. That will be 7,000. But instead we will get either this value or this value, because we are allowing them to happen concurrently, and that is not the way to. So this kind of problem, like updating a bank statement, should be atomic, and the part of the code which update this bank statement, we call it critical section. So we came across, so what is the rule for critical section, that this has to be done singularly, only one at a time. Suppose there are more than one processes, P1, P2, P3, only one process at a time can enter the critical section, that is update the bank statement and then leave it. So that is how we define critical section, a part of the code which has to be like used atomically one at a time. So if we do it one at a time, like first T1 completely happens, then T2 completely happens, then the code will be updated correctly to 7,000, this data. So that is why critical section came into effect. Now we came into some certain properties. So how to solve this critical section problem? So we will this week we will go through very many software constructs as well as algorithms which has been used to solve this critical section problem seamlessly. So any critical section problem should have these following properties. One is mutual exclusion, that if a process PI is executing its critical section, then no other process can be executing its critical section. So basically that means is, so when one is updating the, so only either P1 will be entering the critical section, and when P1 is in the critical section, that is this update bank statement, P2 and P3 cannot be accessing this part of the code, right? So that is your mutual exclusion. Then comes your progress. So in progress, if no process is executing its critical section, then there exists some process that wants to enter the critical section. Then the selection of the process that will enter the critical section cannot be postponed indefinitely. So what does that mean is, if no one of P1, P2 and P3 are inside the critical section, then the OS must allow either one of P1, P2 and P3 into the critical section statement. So initially they are all in ready queue. So initially they are all in the ready queue. So the OS must select one of the process when none of the process are in the critical section to enter into the critical section. That gives your progress. Last one is your bounded wait. So a bound must exist on the number of times the other process are allowed to enter the critical section after a process has been made a request to enter its critical section and before the request is granted. So this means that so you have this let's say P1 is currently in the critical section. Now P2 arrives. Now let's say P2 arrives. Now P1 is currently in the critical section. Now P2 arrives. Now the bounded wait means that P2 that there should not be an indefinite gap when P2 arrives and P2 is allowed to enter the critical section. That means once P2 has arrived, at some point P2 must be allowed to go inside the critical section once, let's say, P1 has completed it or not. The wait between the schedule of P1 and P2 should not be indefinite. So that gives you the bounded wait problem. That gives you the bounded wait uh, problem, property. So, any doubt regarding these three problems, these solution properties, that is mutual exclusion, progress, and bounding weight? Like all the along this like next few minutes, all the problems we will discuss will have some of these properties have been there or may or not have there. So it is always better to understand with what are these properties, this mutual exclusion, progress, and bounded weight. Okay, so uh, now let's look at some of the solutions. So one solution is this Peterson algorithm. So this is a software solution. Solutions to the critical section problem can either be a hardware solution or software solution. So Peterson algorithm is a software solution. So each process will have two variables, this turn and flag. So the turn indicates whose turn is it to enter the critical section, and flag indicates if a process is ready to enter the critical section or not. So if flag I is equals to true, implies that process I is ready to enter into the critical section. So let's look at the code. So this is the algorithm for process P1. So flag Pi is equals to true, flag turn is equals to j, while flag j and turn is equals to j, this will be a wait. This will wait. This is a while loop, and this while loop will wait. What does this mean? This while flag j and turn is equals to j. What does this mean? This means that the currently it is process jth turn to enter into the critical section, and flag is j. That means flag j is in the ready state. So when this is true, process Pi cannot enter the critical section because currently it's j's turn and j is ready to enter into the critical section. So once either of this, so when we come out of this infinite loop, once either of them is false, only one has to be false. So either it becomes ith turn, or j is currently not ready to enter into the critical section. So either of the satisfy condition becomes false, either of this condition becomes false, it enters the critical section, then it computes it, then it makes that okay, now my turn is over, flag I is false. That means I am not ready to enter the critical section again, and then it computes the remainder of the section. So this is for process Pi. So this part is clear, like how a process enters into the critical section and gets out of it. So any doubt regarding this algorithm, because this is important.
When the flag I is turned false, like what does that mean?
Yeah, so flag I is turned false means that it doesn't have to enter into the critical section anymore.
Okay, so but it is said that PI has to enter the critical section many a times, right? Because it has to.
Yeah, so see the first statement, flag I is equals to true. That means flag I is true. What does that mean? That means the first statement, flag I is equal to true. That means it is ready to enter into the critical section, and turn is j. Okay. So while flag I is j, that means j is whether if j is in the critical section, or it is j's turn to enter into the critical section, and then j's turn into the critical section, then only I has to wait. So even though I is ready to enter into the critical section, currently it is not his turn to enter into the critical section. No, critical section is common to both of them, right? So it is a common part. So each process the same part of the code, right?
Yeah.
So process is basically a program in execution. So every process is basically the same program that we are running. So the critical section is that part of the code which has to be atomic. Like example, I talked about the bank transaction part, where the update of the balance has to be atomic. Otherwise, there will be the garbage values that could be stored in your bank balance.
But there, when that one process was reducing 1,000 and the other process was reducing 2,000, that
Yeah,
reduction was a critical thing, right? So
yeah.
every process
No, 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 no.
will have
So
its own critical thing.
no, no, no. Every process doesn't have its own, like, so you need to think about it. The part of the code that is in execution is common to both. So what I am saying is that reduction uh, is different. But think about it. You have written a if condition, and there are particular problems regarding that if condition, right? Let's say the process that PI is running. Let's say it is a process for the transaction type is your like transaction type is basically a online transaction, the online transaction of for your basic needs. Let's say you're buying a biscuit that has 1,000 cost, or let's say you are buying a soap that has a 2,000 cost. So that cost can be part of the same code, but and that is part of the same critical section, but like that doesn't mean that they are different critical section. They are the same critical section.
Okay.
So consider it like this. Consider the critical section of the bank advance statement like this. So update balance x. So this could be a common code, right? Where update balance is basically a function call. Where update balance is basically a function call. Function call with value x. So for P1, the value may be 1,000, and for P2, the value may be 2,000. Now you understood that it is the same part of the critical section. It is the same code for the critical
Yeah.
section, but the data
The
variables are different.
reduction of the balance is the critical section.
Yeah, so update balance is basically so let's say let me rename it. Let me rename it as
Yeah, understood.
uh, debit balance. Okay, so basically the code is same. That will be just decreasing uh, balance minus x. This would be the basically the code which is common. So that only the data variables are same. So it is the same critical section which is applicable for all the process that are running. That's what I basically meant. So if you now there is any problem. Now you
Yeah,
understand this code. Now you understand this code.
yeah.
So basically you are able to enter the critical section only if either it is your turn to enter the critical section, or uh,
The
you are in the run.
flag is
Yeah. So basically either the J doesn't want enter into the critical section. So that are the two conditions. So this becomes false only when it is the ith turn, or J doesn't want to enter into the critical section. So that's the whole thing, nothing more. Okay. So let's so mutual exclusion happens, right? Right. So mutual exclusion happens that only me. What is mutual exclusion? Only one process can enter into the critical section. So here PI enters the critical section only if either flag J is equals to false, that J doesn't want to be entered into the critical section, or it is the turn of I. Okay. Does progress is satisfied? Is progress satisfied? Think about it. Is process satisfied?
Yes,
Why?
because when flag I is turned false, that turn equals to j is already there, and when flag
Yeah,
I is
yeah.
like either one of them is
Yeah,
ready.
obviously, always one of them will always be able to enter into the critical section, because if you look at the code, uh, if you look at the code, that this turn will all this whenever we call this flag, that flag, suppose flag j is equals to false, it will always be able to enter into it. Either one of them becomes false, one has to will be able to enter it. It is not that none of the processes are free. So let's consider the situation like this. So you have this critical section, both P1 and P2 are not have not entered into the critical section and are currently idle. What happens? Uh, what happens in the first two lines? Flag I becomes true, flag j turn is equals to j. So it becomes like this. Flag 1 is equals to true, flag 2 is equals to true, right? And turn is equals to 2, turn is equals to 1. So whenever any one of them reaches the critical section part, so the condition here is for P1 is while flag 2 and turn equals to 2, right? Right. So currently when no one is in the critical section, so what will happen? This one is true currently. Now is this one true? Is this one true?
When nothing is there in the critical section, then it is not.
No, because P2 is turned is equals to 1. It has turned 2 equals to 1, right? So this will becomes false. So obviously P1 will be allowed then to go into the critical section. So like the first this part of the code has been executed and this part of the code has been executed, right? So at this time what happens? Turn is equals to 1 after this part of the code has been executed. Even though this is true, this is false. So one of them will always enter the critical section. So progress is bound to happen. And the last one is bounded weight. Is bounded weight satisfied? So what is the bounded weight condition? So suppose if process P1 is entered the critical section, then and P2 is ready, that at some point P2 should be allowed into in the critical section. Like it so let's say you have these processes P1, P2, P3. So P1, let's say, is in the is currently in the critical section. So when P1 ends the critical section, let's say suppose P3 enters the critical section. When P3 leaves, let's say P1 enters. So if this thing happens, that though P2 is available, P2 is not scheduled, that is not bounded wait satisfied. So P2 should be scheduled at some point, right? That is what this statement means. Now, does the current Peterson solution allows bounded wait? Does this solution allow bounded wait?
Yes,
Yeah.
every time it is either of them getting
Yeah.
inside, like
Uh,
getting
it satisfies bounded wait that either even if for more than two processes or three processes, and this algorithm which you are seeing that could be this is specifically for two processes, but it can happen for more than two processes also. The trick is the trick is this flag and the turn variable. So this maintains that there will be a fair way of scheduling these fair way of scheduling if there are more than one process available and they want to enter into the critical section. So in the future solutions, you will see that this fairness is not there. So this flag I and turn is equals to j. Uh, this is quite so if there are three processes, then it would be flag 2 and turn is equals to 2, and flag 1 and turn is equals to 2. So that will be a big complex condition. But the trick is this flag and the turn allows that there is a fair weightage for each process to get into the enter into the critical section. So when 1 is not there, 2 will be there. If 2 is not there, 1 is will be there. And similarly, if it, the case for P1, P2, P3, if there are three processes. So that is the trick that this Peterson algorithm uh, utilizes. Okay. So any doubt, any more regarding Peterson algorithm? Anyone, any doubt regarding Peterson algorithm? Okay, what is the problem with this Peterson algorithm? Because nobody uses this. So the problem with Peterson's algorithm is this if while condition. So while P1 is not able to go inside the critical section, it is still utilizing the CPU cycles. Like it is continuously running this infinite while loop, that whether the flag has been turned on and on, turned on or off, what is the current turn variable. They are continuously checking it, which is a very wastage of computing resources. Like one continuous check always, that is a loss of computing power. So that is something which is termed as basically your this busy wait. This is called busy waiting. So what does this does is it continuously waits this on a while loop to check whether it has been the turn variable or the flag variables has been correctly satisfied or not. So that is a very bad way of doing a program. So as a result, Peterson algorithm, though it satisfied all the three conditions for like for critical section problem, it is very inefficient because of this bounded wait problem. Because of this busy waiting problem. Okay. So uh, so so now arrives the another way of doing it. So the solution is basically locking. So somebody acquires a lock, then it enters the critical section and then releases the lock. This is another way of solving this critical section problem. So you take a lock. It is like your normal lock and key mechanism. So you acquire a lock, and then you lock the part of the code, and when your job is done, you release the lock. This is another way of critical section problem solving. So this can be done for both hardware and software. So uh, so for hardware, there are two types of instructions: test memory, word and set value, swap contents of two memory words. For hardware, so whatever code that you will find here is basically hardware codes. These may look like a software algorithm and all, but these are actually done in hardware using low level languages. So, so what does this test and set do actually? So what does this test set and do actually? So it has this log variable which has been initialized to false initially, and this statement is quite common, right? So it, it is the same infinite loop thing, that busy waiting thing. So as long as this log has not been acquired, you stop. When the log has been acquired, you enter into the critical section, then make the log false, that is releasing the log. So this part is acquiring the loss. This test set and log is acquiring the log, and this is releasing the log. So if you have a difficulty understanding, consider this as a very higher level of this Peterson algorithm, where you have in Peterson algorithm you have to remember these variables that were I have used some flag, I have used some turn variable. Here you don't have to remember anything. You acquire you There are two parts: one, you acquire the lock, and two, you release the lock. So this lock equals to false is release the lock, and this test and set ampersand log, basically acquiring the lock. So how do you acquire the lock? So this part of the code basically acquires you the lock. So how long is this? When it will remain in this while loop? How long it will remain in this while loop? And until and unless this becomes false. So initially the log value is false. Fine, false comes here. Return value is kept as false, and the uh, target value becomes true, and the return value is false. So if you have any difficulty understanding this, you just think about this. Say returns the original value of past parameter, set the new value of the past parameter to true. So basically this happens in it. So you have a, let's say, a register, and then you have a log value. Now this is your acquire statement, and this is your release statement. What does this lock means? Let's say lock initially is equals to false. So if P1 wants to enter into this critical section, so it acquires the lock. What it does is, it initially it was false, so it run this test and set code. What it does, so this acquired lock, so it enters into the critical section only when the acquired lock is false. So so it comes here, acquired lock is false, it sets it to true, and it enters into the critical section. What happens in the release? It changes its value back to false. This is basically what is happening, nothing more. Is basically setting the register value true or false. Whenever one wants to acquire the lock, it changes value to true, and whenever it releases the lock, it changes its value to false. So when some other process, let's P2, arrives, and it comes to this acquire portion, it checks here, and it says that the log value is currently true. So when the log value is true, this will remain in the busy waiting loop, and when they release the lock, this becomes again false, and they enter into the critical section. This is basically what happening in this test and set part. If you don't understand the algorithm or the part of the code, this is simply what is happening in that part of the code. Any doubt? right? So this part is always this part will be in the busy waiting loop as long as this part returns true, but if this lock is false, it comes inside the critical section, and it turns at the when it comes into the critical section, it makes the lock is equals to true, right? Any doubt? Any doubt? So what about the properties of critical section problem? Is mutual exclusion satisfied? Is mutual exclusion satisfied?
Yes.
Yeah. So why mutual exclusion is satisfied? Because when one process P1 is inside the layer, there are two processes. Uh, so if there are two processes, let's say P1 and P2, when P1 is inside the critical section, is inside the CS, this log value is basically true, and at that time uh, P2 will be in busy wait in the while loop, because that while loop condition is true. Now when it leaves the critical section, it turns this log value equals to false. So at that time it comes out of this critical section and enters the comes out of this BC loop and enters the critical section. So mutual exclusion is satisfied, and as well as progress, because you see one goes and one arrives. There is nothing that it has to like it cannot go inside or not, right? So mutual exclusion and progress is satisfied. Now what about bounded weight? Is bounded weight satisfied? Is bounded weight satisfied? Yeah, if you say yes, you just give me the reason. If you say no, just give me the reason.
Uh,
Yeah, so why no?
once the lock is acquired,
Hmm.
uh, once the process doesn't terminate, it will not change its
Yeah, so
false.
the problem is when I release the lock here, there is no there is absolutely no way you know. So if there are three processes, which of P1 or P2 will enter into the critical section? There is actually no priority given, right? There is no algorithmic way given that which one of P1 or P2 will enter into the critical section. It may happen that P3 enters, and after that P2 just remains there. P3 enters, and then P1 again enters, then again P3 enters. So there may be a chance that P2 just waits randomly forever. So this does not satisfy bounded weight. And again it comes back to that interesting thing of the Peterson algorithm, which has this turn variable and this flag variable, which basically maintains a order in which one can go inside the loop or come outside of the loop. But here there is nothing such there, so it will be very random. So if P1 exists, either P2 or P3, anyone will go in, but there is no order in which P2 and P3 will come go inside the critical section. It may be that P2 waits forever to go inside the critical section. So bounded weight is not satisfied. Clear this one? Okay. So Okay, so now if you want to make it, so let's come to the part, like if we want to make it bounded weight with test and set, what you will do is you will use this waiting time part, this waiting part, and this thing called key. So if you go through this code actually solves that bounded weight problem. Now it is a complete critical section solution. So this waiting symbol will make sure that a proper order is maintained in which the values, like in which the process enters into the critical section and comes out of the critical section. Right, they do such stuffs and all, locks and all. So if you follow this code, this is basically what like how it happens. So basically if I give you a short example, so it happens like this. So you have a queue of waiting process queue. So P2, P3, P4 are waiting here, and one by one each one will get the lock, and there is a complete algorithm, like algorithmic way, each one will get a fair share of getting inside the critical section, and that's how bounded weight is satisfied. Okay, so please after the class, please go through this algorithm and try to understand how bounded weight is satisfied. The absolute way to satisfy this bounded weight, basically the key is this waiting array, waiting list, that will satisfy it, that will satisfy this bounding weight problem. Clear? Any doubt regarding this bounded weight mutual test and set problem? Any doubt so far? Any doubt so far, if you have? Okay. So this compare and swap are quite similar to that like test and set instruction. So I will request you just go through it in like after the class. So this is quite same. Like this solution also results in busy waiting. If you see the code, it is basically the same. While there was test and set, this compare and swap, nothing more. It is quite basically the same. Okay, so now these were hardware solutions. Now let's come to the software solutions called mutex. So for logs there are two parts. One is acquiring the log and is releasing the log. So these two operations are done in mutex like this. So for acquire, if we call this function acquire function, this happens. While not available is a busy wait. Then when the busy wait ends, it turns the available is equals to false. That means now the critical section is not available anymore. Now the critical section is not available anymore, and for the release it just becomes lets that critical section is available. Okay, so basically it's like this. There is a available variable. These are software solutions, by the way. So if it is true, that means process can enter the CS. Process has to wait to enter into the CS. Right. and the code is quite similar to like the test and set. So just for while not available, it's a busy wait, and then when available becomes, when this becomes false, that means someone has released it. So available becomes true, then it turns the available equals to false and it takes it to the critical section. Any doubt regarding this part of the code, like how, why you are able to enter into the critical section and all? So basically, this is what we have actually for available and request. So initially, let's say P1 and P2 has arrived, and available is equals to T initially. So which one of the ever comes to the acquire first? This becomes false, so it doesn't have to busy wait, and that makes the available equals to false. So now if P2 tries to enter, P2 does the acquire, what happens in this case? It goes into this busy waiting loop. It goes into this busy waiting loop, right? And when it comes out of the busy waiting loop, when P1 does the release, which is make the available equals to true. That is your mutex. So any doubt regarding mutex? Okay. So this is your typical um, acquire lock and release lock part, the normal critical session code. So again, so does mutex provide mutual exclusion? By now, you should understand what I am talking about this. Does this code support mutual exclusion? Does this part of the code support mutual exclusion? So this supports mutual exclusion. Okay, so only one process can enter into the critical section. So this one is satisfied by this available and non-available part. Progress is also satisfied, that always if none of them is in the critical section, then one will always be added into the critical section. Now, is your bounded weight satisfied? uh, Again, your bounded weight is not satisfied here, because when you make when you release the log, when you make available equals to available equals to true, at that time any one of the processes in the waiting in the waiting in your busy loop, this acquire busy loop, this acquire busy loop, anyone, like if P2 and P3 both are in this busy loop, at that time only one will be able to enter into the critical section, and it could be very random. There is no choice which can enter into the critical section. So again, this is not a bounded weight solution. Okay, so busy waiting is still happen. Uh, Busy wait is still happening. Now let's come to the other part, semaphore. So semaphore is basically uh, uh, more sophisticated, like it does the same kind of things as mutex locks. But remember about semaphores are basically variables, basically two individual variables that can be accessed by these functions wait and signal. So 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 if you see previously, so what is the difference between this wait code and that acquire code? Anybody? What is the difference between this wait code and that acquire code? So here is the wait code and here is the acquire code.
It is updating
Yeah.
the yes.
While previously you are applying only one. While previously we are applying only one lock, like only one. Let's say what I mean to say, where only one variable available as true or false. Here, we are using a variable to denote it instead of. So, if s is less than equal to 0, that means that means what? If s is less than equals to 0, that means someone else is using the critical section.
Critical.
Yeah. And then you make s equals to s minus 1. So when you come out of this critical, when this loop breaks, when s is 1, 2 or 3, such kind of values, the loop breaks, you make s equals to s minus 1. And the signal part is similarly that. When you have entered in the critical section, that means s equals to 0, s equals to 0 or something, you just simply increment the s value as s plus 1. Now here is the main fundamental difference that comes from mutex. So mutex, so here you are using a variable, uh, s, which can have any value. Now consider the case s equals to 1. Consider the case of s equals to 1. So you have this wait function, and let me write it. While s less than equals to 0, busy wait is equals to s minus 1, and signal s is equals to s plus 1. Okay, so consider the special case when s value is 1. This is called binary semaphore, and this is basically is exactly equivalent to your mutex in function. Why? Because if you look at the critical section problem, when s value is 1, so s value can be 0 or 1 in binary semaphore. What happens in that case? Initially, the value of s is equals to 1. So when p1 arrives, so suppose there are p1 and p2 processes. When p1 arrives, the value is s equals to 1. It goes to the wait. It doesn't wait here. It changes the value of the s equals to 0, 1. It becomes 0. It enters in the critical section. p2 has to busy wait here. p2 has to busy wait here. p1s come inside. p1s exit the critical section, and it changes the value to s equals to 1, and then p2 is no more in this busy wait loop, and then it enters in the critical section and it becomes s equals to 0. So at a time, only one process is in the critical section. That means mutually exclusion. So this is the property is exactly similar to how mutex works. Uh, so now the question is, why then we have a semaphore and a mutex? If both are the same functions, then why do we have a mutex and a semaphore, right? This will be a valid question, right?
Boundary waiting.
Not bounded waiting. Okay, so these binary semaphore and mutex are exactly same, but the trick for semaphore is basically you can have more than one value of semaphore. So let's say
Yes, right.
that semaphore value can be 10. And if you ask me why it is required, why is it very useful? Because if s equals to 10, that means 10 processes can enter cs simultaneously, right? If s equals to 10, what does it mean? 10 processes can enter into the critical section simultaneously. But the law of critical section says that mutual exclusion should be guaranteed, but this does not satisfy mutual exclusion, right? So why this is required? So in some problems, like we will come afterwards, like consider you have a problem, this classical problem of reader and writer, where there are one writer and there are more than one readers. So reading from a paper, like a piece of file, by 10 different processes should be allowed, right? Because reading is not an atomic process. Even though they are reading the same piece of the code, it should not be an atomic, it should not be an atomic process. Like what I mean to say. So let's do the reader writer problem first. Okay. So a reader writer problem is, consider you have one writer and 10 readers, and you have, let's say, a file. So consider this situation. Reader, one reader is reading the file. Should a writer be allowed the file? Uh, so give your views on this. So a reader is reading the file. Should a writer be allowed at the same time to write into the file? Give your views on it, general views. Like, I suppose someone is reading a file. Okay, so our computer program is reading a file. Should a writer program be allowed to write in the file simultaneously? Come on, like you can share your views. Like this is supposed to be an interactive class.
No.
Yeah, because at that time that means whatever I am reading, that will be get corrupted. So I might be reading a old value, but I am supposed to read a need new value, right? So writer is writing something new value, but I want the old copy, right? So I this should not be allowed. So here you need a mutex, right? You need a mutex between these problems. So a writer and reader should not operate at the, sorry, I got disconnected. Sorry, I got disconnected. 1 minute. Yeah, is it visible? fine. Yeah. So a mutex lock is required here when one writer is reading the file, reader is reading the file, and the writer comes. Okay. So a mutex lock is required here. Okay. Now say uh, one reader is reading a file, and let's say one more reader appears. Should that reader be allowed to read the file?
Yes.
Yeah, yes, because reading is not mutual exclusive required, right? So you should be allow it your reader to read the file. That should not be a constant. So here, no mutex lock is generally required, but you may put as something like this, that 10 readers max. Suppose you don't want to overload your system, you say that only 10 can at a time read the file. Okay, so the here your counting semaphore, this is a quite good example of why this counting semaphore, or n equals to 10 is required. There will be more such examples. This producer consumer problem, where one producer is producing, let's say, 50 items. So you need to check whether the glass or the queue or the list has been completely filled up by the producer or producers or not, or the consumers have completely consumed it not. So there, that kind of situation, counting semaphore is required. Okay. So that is your basically counting semaphore. That is basically your counting semaphore, where an integer value over an unrestricted domain. So it is not mutually exclusive, but it is not meant to be mutually exclusive. Counting semaphore's requirement is something different. Okay. So again the busy waiting part appears. Okay, so you are again busy waiting on this thing. So you need to get rid of this busy waiting. So what you will do? So you will basically maintain a list, maintain a list of processes. So at the end of the day, everything comes to a list. You need to maintain a list to make sure that that whatever processes come, you enter into that list. So basically, a semaphore is implemented like this. You have a structure where you have the value of the semaphore. It can be a 0 or 1 binary semaphore, or more than one like n counting semaphore, and as well as a process list. The process list will contain the processes that has requested the semaphore. So there will be two operations: block. So block will place the invoking process into this queue, into this list, and wake up will take the process out of the list. So by this time you have got the general idea. Like, so most solutions, like after Peterson's, whatever you have seen, test and set, swap and test, and those kind of things, and as well as these mutex and semaphore, all doesn't satisfy bounded weight. But to make satisfy the bounded weight, what you do, you maintain a list. You maintain a list to satisfy it. So whenever a new process comes, you enter which, and it doesn't get the lock, what you do, you just enter into the waiting queue. And when your critical section, the process that is entering into the critical section, leaves the critical section, it just does a wake up call. Okay, now my thing is done. One of the process that is in the wait list, you can come outside and enter into the critical section. As a result, your this bounded wait, or the busy waiting thing, is satisfied. Is just not more wait problem. Okay, so this is how your busy wait is satisfied. So if you see like this, So semaphore value is decremented by 1 and this process is added to the S list, and then you block it, and the signal process is basically you remove the process from the S list and do a wake up. So there is no more while loop. So infinite while loop is gone. Any doubt so far, semaphore? Make sure these concepts are clear. Like these are the main topics of operating systems, which are very difficult to understand. But once you understand it, you will never forget. Like scheduling was one that is very common in your competitive exams. Semaphore and these things are one another part. Then next week you will come across deadlocks. That will be another very crucial part, which are very commonly asked questions. Okay, so semaphore, you see how busy wait is removed from semaphore. Now, does the implementation ensure progress? Does the implementation ensure progress, and does it ensure bounded wait? So this busy waiting part, it basically, if you see here, this block and wake up, there is nothing that specifies how this block and wake up occurs. Like you add it to the list, but there is no order in which you wake up from the list. Okay, so that is why bounded wait is not satisfied. Okay, so you remove the busy waiting part, but the bounded wait is not still satisfied because it is have no clue. The block or the wake up is no clue how to remove the element from the array. Whether it will be a stack kind of implementation where the first in last out, or queue kind of implementation when the first in first out. That is nothing specified. So it is bounded wait is still a problem here. Busy waiting is no more a problem. But what about progress? So let's consider this situation. So you have let's consider it like this for let's say mutex and binary semaphore. Let's say in logs in general, you have an acquired log, you have an acquire, you have an acquire and a release. Okay, let's consider P1, consider P2. Now let's say it has two semaphores. Let's say S1 and S2. These are two different semaphores. Okay, so let's say P1 does this, acquire S1, acquire S2, acquire, let's say, release S2, release S1, and it does something like this. P2 does something like this, acquire S2, acquire S1, release S1, release S2, and here is your critical section. Now, what happens in this case? So we are discussing whether progress is satisfied or not. and you have these semaphores S1 and S2. So what happens in this case? So let's say initially both are 1. So when P1 and let's say we are these two are occurring concurrently. So P1 happens, P1 acquires S1, like so S1 is available. So S1 is acquired by P1. Similarly, log S2 is acquired by P2 because S2 by P2 because S1 is available. So this balance becomes 0. Now it comes here. What happens? P1 will wait on here. Why? Because it's trying to acquire S2, but S2 is not available. S2 is currently with P2. Similarly, here P2 will also wait because it wants S1, but currently S1 is available with P1, but it doesn't have, it cannot S2, so it will again wait. So, as you see, both are trying to acquire two different semaphore variables which are not available, and that log has been acquired by one each other differently. So as a result, they will just wait here and they cannot enter into the critical section, even though nothing is there in the critical section at this point of time. Low element is there in the critical section at this point of time, right? So is progress happening here? Is progress happening? Yeah, so progress is not happening. So the problem is, okay, with one semaphore it's okay, progress will happen, but when you are using two different semaphores, you see one lock has been acquired by P1, another lock has been acquired by P2, so both of them cannot enter into the critical section. So as a result, this condition is called uh, deadlock. A deadlock, and it gives rise to starvation because both want something different and they are not available to it. So this lock is dead, it cannot move anyone forward, and they are basically starving for the resources that they need and they don't have. So another example of this kind of deadlock or starvation is basically when a priority inversion, when scheduling is happening and a lower priority process has acquired a lock, but but now a higher priority process has come and it wants to acquire the log, but the log is currently with the lower priority process, so it cannot get inside the it cannot get inside the critical section and it has to wait even though it is a high priority process. Okay, so that is the issue of deadlock and starvation. So now it's clear that why progress is not happening. Okay, so another problem with semaphore is this: you need to maintain these things like signal and wait. So you have to put a signal first and then only we can put a wait. You cannot put two waits. So it's a very messy kind of thing that you need to maintain a lot of variables and all. So so one solution is, so it's basically a messy kind of way of operations. If you are using a semaphore, you need to maintain that. You need to remember while programming that, okay, now the mutex value here can be something else. So it can be 0. What will happen if I put the mutex value here and all? If there are more than one mutex you have, suppose you have written a if conditions. So suppose you have written some if conditions. Uh, So suppose you have written, so this is your critical section, and you have entered into the critical section through here, but there are many if conditions and loops here, and the exit from the critical section may have various different paths. So if you are, if you have done a wait here, you have to put signals in all these different paths for sanity. And you have to program it, like when you are writing the program, you have to maintain this thing, that we have to make sure that all of the paths of the exit from the critical section has been covered using the signal. So it's a very messy way of programming, and as a result, people don't use semaphore that much for regular usage, which comes us to the next solution, that is called monitors. So what are monitors? So monitors provide a much higher level of abstraction than this. You have seen, first you came across the hardware solution, that is test and set, swap and load, those kind of things. That was in machine level language. Then you came the mutex. Now mutex is for uh, like one lock and all. Then you came across semaphore, 0 and 1 semaphore. Then you came across in counting semaphore, and now you are coming at the top level of it, that is the monitor. Monitor is a very like, have you done object oriented programming, right? So I so even if you have not done object oriented programming, you have done C programming, where you have used function calls, right? For various operations, like you have written a calculator program. So let's say you want to do a multiplication, you call the function multiplication and do it for in number of numbers and all. So monitor is such a kind of abstraction that has been provided for this convenience for process synchronization. So you will have a monitor name and the shared variable declarations, and the list of procedures are basically the shared variables, and then you have some initialization code. So uh, this is the schematic view of the a monitor. So there is an entry queue. So only one process can enter the semaphore one at a time and do these operations, and then it can leave the semaphore. Condition variables need mechanism to allow the process wait inside the monitor, provide condition variable. So basically there are these operations, those basically your operations are wait, signal, those kind of things, and there should be some conditions. So you all you need to do is maintain this condition variable. So this condition variable, so a process invokes the operation, so x equals to wait. So when the condition x is satisfied, then only this wait is called. That what it means. So let's look at some choices of semaphore and all. So this is your monitor. You have your critical section. So processes enter into the monitor in some queue, and when the job is done from the monitor, it comes out of this queue. Now you have these variables, functions, wait and signal. It basically does the same thing that you have done in semaphore. So some condition variables, so some critical section code is running, So it waits on this CS, and when this is done, it sends a signal. So the signal is basically put someone else from this queue into this monitor and let me go out of this monitor. That basically what the signal does. And wait is basically used to come inside the critical section and achieve it. Now, uh, if you look at this, you might think that okay, how is the concurrency happening? Because the entire code is inside the critical section. Or is the entire problem is in like only the critical section is inside the monitor, or the whole program is inside the monitor? Right. So the trick is the entire program is in the monitor, but only the critical section part is very important. So you allow more than one process inside the monitor, but if you encounters a wait and it is not able to insert into the critical section, it sends it to a different queue. So wait queue. Let's name it wait queue. Right. So it it sends it into the wait queue. So like P3 has been sent into the wait queue because P2 is currently in the critical section, and P3 is here. So when P2 leaves this critical section, what can it do? It has two options. Either it releases one from the wait queue, or another one it releases from the wait queue. And also, uh, uh, the rule is only one can be inside the this monitor. So when it relieves the critical section, so does it should it be allowed to go beyond this? So there can be more than one signals and all. The answer is no. So when P2 leaves the critical section, it has to go back here if there are other parts of the code that is remaining here. So that is how your sanity is maintained. So there are more such queues are maintained. So not only some one wait one, let me call it a wait one queue. There are more such queues here. So these wait and signal are done simultaneously. So either the signal can make sure that you put someone from this wait queue to here, or you put someone from here to here that is not inside the ready queue. There may be a ready queue there. So when the process P invokes X signal and process Q is suspended uh, in X wait, what should happen next? Both Q and P cannot execute in parallel. If Q is resumed, then P must wait. So there are two options: signal and continue. P either waits until Q leaves the monitor, or it waits for another condition. So this can happen. So P either waits until Q leaves the monitor, or it waits for another condition. So P moves from the uh, working state into the wait queue. Another option is Q either waits. So P doesn't have to wait. P either waits until P leaves Q either waits until P leaves the monitor, or it waits for another condition. Right. So is this diagram clear? Like if you have understood this diagram, those these two conditions won't be a issue for you. These two conditions won't be an issue for you. So let me know. I will do it again if you want me to draw this diagram and display it. Should I do it again?
Yes, sir.
Yeah. Okay. I will do it again. So your monitor, consider your monitor as a high level programming execute. Okay, so your entire code, whatever you have written, is inside this monitor, and there is the critical section as always. The rule is, so let's call this your ready queue, or let's say let's rename this. Renaming is the best option at this case. Your in queue, and this is your out queue. This is your monitor. Here are your uh, here is your critical section. Here is other lines of codes. Here is other lines of codes, and here is another code called wait queue. Here it says the processes P1, P2, P3, P4 dot dot dot. Okay, so let's say P1 comes. Uh, it's enter into the critical section. It completes into the critical section and it comes out. Now let's say P2 comes. Let's say P2 comes. Now let's say it waits on some condition variable. Okay, so you have this wait function and it has so instead of the binary or counting semaphore here, P2 waits on some conditions that okay, so my let's say P2 is a uh, like you have this reader writer problem, right, which we discussed before, where so suppose there is nothing written, what will the reader do? Suppose there is nothing written, what will the reader do? So it has to wait, right? Or consider the uh, producer consumer example. You have a producer and a consumer. Producer produces item, pushes item, let's say in a queue, and consumer consumes item from the queue. So producer's task is to put items into this queue and consumers enter items into the queue. So suppose so first process, let's say, was a producer one, and the second process, let's say, was a consumer one. So and the third process was again, let's say, a consumer one. So producer produces P1, it leaves the critical section and done. So that is one item on the queue, right? So next is C1 comes, C1 consumes it and it comes out of the loop and it done. Now let's say C2 comes. Does there is anything in this queue at this point of time? Because P1 produced, C1 consumed. That means buffer is 0 at this point and C2 has arrived. What will C2 do? What will C2 do? C2 has to wait for some producer to arrive, right? So what will do in that case? It cannot enter into the critical section. What will do? It will wait in this queue. C2 will wait here. Now let's say P2 arrives. Let's say P2 arrives. Okay, now P2 arrives. P2 uh, P2 runs this code. It enters into the critical section and it comes out of the critical section. Now here here is the wait and here is the signal part. Okay, let's say. So does P2 has to wait? No, because there is no producer at this point accessing it. So but it changes the buffer value to 1. Now it comes here in the signal part. What options that P2 has? What options P2 has? P2 can either say come P3 enter into the buffer, or it can say come C2 consume from the buffer, right? It has these two choices, right? It has these two choices. This part is clear. It has these two choices. P2 has these two choices. Either tell P3 to come and enter into the monitor, or it has to say the wait queue. Okay, come C2 now, come and consume your food. It has these two choices. Now another problem is, what does after this signal what is the procedure we follow after this signal? So do suppose let's say C2 have the chosen part is C2. Let C2 come and consume it. Now you know in a monitor one process at a time. Then what will P2 do? Well, either will P2 uh, execute this rest of the code and after that we allow C2, or P2 says that okay, I am going into the wait queue, C2 first you consume, then I will you go and come out of this wait and then I will use it, and then I will again enter. So this is your, these are the two options your P2 has when it calls the signal. So that is what it has said here. P either waits until Q leaves the monitor or it's wait for another condition, signal and continue. Q either waits, that is the second part, until P leaves the monitor or it waits for another condition. Now it is clear. Now it is clear.
Yes.
Sneha? The main part is that when you like I know that they have in the slides they have gone for this producer consumer and reader writer problems at the end, but when you consider it through this prism, that producer consumer prism, like why there will be different conditions and all, then you will understand that okay, producer is performing something different and consumer is performing something different. It balances on two different conditions. Producer's condition is whether buffer is full or not. Consumer's condition is whether buffer is empty or not. There are two different conditions. So there you need a queue of this wait comes. So these are the options you have: signal and wait, and signal and continue. These are there is reasonable arguments in favor of adopting either option, since like these are the things. So a compromise between the two choices were adopted in the language concurrent Pascal. When P executes the signal operation, it immediately leaves the monitor and Q is immediately resumed. So many programming languages have accepted this kind of notion. So how you implement a monitor? Okay, so monitor is an abstract high level format, but you need to implement it something, right? So if you look at this diagram, there are basically two queues. So this in and out queue, and there is this wait queue. So you need to maintain basically two mutex, one for this and another for this. So you need to maintain these two mutex. So a process execute wait mutex before entering the monitor and must execute signal mutex after leaving the monitor. Since a signaling process must wait until the resumed process leaves the monitor or it waits, and an additional semaphore next is used. The signaling process can use the next to suspend themselves. So integer variable count next is provided to count the number of processes suspended on next. So your mutex is here and your next is here. So you basically use two different mutexes for controlling two different queues, nothing more. So this is how you implement a semaphore. So you have the monitor, you have the semaphore mutex, that is 1 initially, semaphore next is 0 initially, next round count is equals to 0. So if next count is greater than 0, signal next, else else signal mutex. So that is basically this. P waits until Q leaves the monitor or it continues for another condition. That is here it is happening. So it signal always signals the next, and if there is no next, then it signals the mutex. So the first option always here is check next. If there is nothing next here, then the next option is here. This is what is the procedure for the monitor. And similarly, the wait operation is similarly like that. If x wait can be implemented like this, if our next count is 0, signal next or signal mutex. Then wait mutex wait same x count minus minus. So basically, if the wait appears here, so either signal one process to come here and put it here, or one process to come here. That is what it means. Show this tab. So either signal the next or either signal the mutex. So always the one in the next queue is given more priority than the one in the ready queue. And here is how the signal is implemented. Here is the how the signal is implemented. Next counter plus plus, signal xm, wait next minus minus. So resuming process within a monitor is first come first serve not adequate. So there is some priority maintained there. This is the resource allocator example. You can have a look at this. Okay. So that ends your monitor part. Any doubt regarding monitor, you can ask me again today. Now I'll be happy to get. I know this is a little complicated, but you need to get the hang out of it, like how to do this. So always remember, for wait and for signal, in both cases you need to give the priority to the next first. If there is no next, then you jump one from the ready queue, and only one can occupy the monitor at a time, irrespective of it is in critical section or not. So this may look a little more difficult than your semaphore, but actually it is much easier in a softer constructive manner, because these you will be given this object like these APIs, and you just have to write your implement your code using the APIs. You don't have to remember how this happens in the background. You will be given the specific APIs, wait and signal, and wait and progress. Okay, so any doubt regarding monitors? Okay, so with that we have come into of the synchronization part. Let's look at some examples of classical synchronization problem. Two I have already given a little bit of uh, introduction, the rewriter problem and your like and your producer consumer problem, like bounded buffer. So let's come to them one by one. So first the bounded buffer problem. So there is a buffer of n size, semaphore mutex. There is a semaphore mutex which is initialized to 1. There is a semaphore full which is initialized to the value 0, and semaphore empty that is initialized to value m. So note these two are these empty and full are your uh, counting semaphores. So mutex and mutex uh, is your general mutex, and this is your counting semaphore, and this is also your counting semaphore. Okay, so you have a buffer of n size. So the job of this mutex is to provide mutual exclusion, and the job of this full and empty is to maintain check on the status of the buffer. Okay, so let's look into it, how it is happening. So this is your producer process. So first there are some random codes here, then you have your first wait, and then you have your empty wait and mutex wait, and then you have your signal mutex and signal full. So what is happening? So initially empty is n, empty is n. So when producer, let's say p1, comes here, so what will the value of n becomes? N minus 1. And with mutex it acquires the lock to produce item into the buffer, right? And then here it releases the lock, and here in signal full what you will do, it will increase the full value from 0 to 1. So let's say again p2 comes concurrently. So okay, so the empty value will become n minus 2, but it cannot enter the mutex, this part of the code, as long as p1 is inside it. Okay, when it is done, it will immediately update the value of full to 2. So note the reason for putting this empty. So why are you using empty and full as semaphores and not normal values? Why empty and full are semaphores and not normal variables? Why? Uh, any answer? Why empty and full are semaphore variables and non-normal variables? Because again, the reason is the update of these counters should be atomic. So these operations, this update of the value of empty or full has to be atomic. So these are maintained to be as semaphore and normal variables. If you are using normal variables, again then update operation which we have which I have given during the band transition example, so that will be corrupted value and recognizable value, let's say, like, which is not what you want. So the buffer may have four variables, but the size of empty and full may be different correspondingly. And why use two different values? Two different elements, empty and full. Why two different variables? Why two different counting semaphores, empty and full? Why? Not one single why. Not one single variable. So again, the reason is because there will be two types of processes. One is producer, which will produce it. Another is consumer. So the producer, check for the producer will be whether buffer is full or not. The check for the consumer will be buffer empty or not. So that's why you are keeping two different variables, not a single variable. Okay. So this check is basically to determine whether the buffer is, this check is basically to determine whether buffer is full or not. So when the buffer is full, empty value will be 0, and then it will have to wait. And here you understand the mutex, that is your binary semaphore, and then your signal. So signal is full, that means a element has been written into the into the buffer. So why this is required? Consider the example of consumer. In consumer, it checks for underflow. So the consumer will wait here if the buffer is empty. Wait if buffer is empty. This part is clear. Your mutex, it provides mutual exclusive to remove an item from the buffer, and here signal empty, that is it signals to the producer, okay, look, I have removed an element from the buffer. That is what, nothing more. So remember this sequence, remembering this sequence unity. So this checks for buffer overflow, whether the whether the producer checks that whether the buffer is full or not. Here it acquires the mutex lock, and then it signals that I have produced something to the consumer. This signals to the consumer that I have put something into the buffer. You see, here it's waiting for the food. So if there was a buffer underflow here, so when this happens, this signal full happens, it comes here and does that buff. Okay, now there is no more overflow, underflow. One element has been produced to consume. You can go and acquire the lock and then come out. Okay, that is the main mechanism of this bounded buffer problem using semaphore, or let's say even you can do it using uh, your monitors. This one is clear. Like, this is the first basic problem of bounded buffers. So there are much more typical bounded buffer problems. Therefore there are, let's say, one producer, n consumers, n consumer, one producer, different priority walls. There are different codes also living in your books, but this is the most important one. So any doubt regarding this bounded buffer problem? So producer first checks overflow, then it acquires the lock, and then it signals that I have filled something into the buffer. The consumer checks underflow, acquires the lock, and then it signals that I have consumed something from the buffer. Nothing more, nothing, there is nothing extraordinary in this part of the code. Okay, so let's next come to the reader writer problem. So readers only, I discussed previously, readers only read from the data set. They does not from all update. Writers can read and write. Allow multiple readers to read at the same time. Only one single writer can access the shared data at the same time. So you have a semaphore, write mutex, initialize the 1, semaphore mutex, initialize to 1, read count, initialize to 0. So this write mutex is used for the so this read mutex is used for reading, read count number of processes that are reading, and this mutex is acquiring the lock. This is the structure of the writer process. It waits, it checks whether is any reading is on. If there is no reading going on, it writes and then signals that okay, you can continue reading again. Now here is the reader process. First it takes a mutex to update the read count. If read count is equals to 1, then it waits. Why? If read count is equals to 1, why it waits? Because nothing has been written yet, so it waits. And then once something has been written, it releases the lock, reading is done, then again it acquires the lock, it releases the read count, and then again if read count is 0, and then it signals that okay, you can do some writing on the file. Okay, that is what it does, and that is it continues. Quite similar to your bounded buffer problem is your reader writer problem. There are many variations. So no reader kept waiting unless writer has permission to it. One writer is ready to perform the writing. There are various such problems there. And there is your dining philosopher problem. So we'll discuss this dining philosopher problem next week. Okay. So let's solve some problems this week. I know there is little time left, but let's do it. So this is the question one. So which of the following is incorrect about monitors? Monitor is a high level abstraction that provides convenient and effective mechanism for process synchronization. True. Monitor is a high level abstraction which provides a process synchronization tool. Multiple processes can be active within a monitor at a time. False. We have seen only one process are allowed to be active inside the monitor. Mutual exclusion is guaranteed inside the operating system by the operating system. True. Internal variables can only be accessible by the codes within the procedure. True. These are all true about monitors. So the incorrect one is this: multiple processes can be active within the monitor. This one is clear. This comes basically from the
Yes,
properties of your monitor. So next, let's come to this one. In Peterson algorithm, if the turn variable is not present, the resulting solution will violate which of the following? Mutual exclusion, progress condition, bounded weight, none of the above conditions.
Mutual exclusion.
How mutual exclusion?
If turn is not given, then it is not giving the
No. So
critical section to change.
no. So if the turn is not given, so if the turn is not given, what will happen?
Even the turn after flag I equals to true. That will
Yeah.
also be
So
considered.
if turn is not given, so will mutual exclusion be allowed?
no, okay.
No.
Why? So I have a process I, process 1 and process 2. Flag 1 is equals to T, flag 2 is equals to T. Right? Now, while flag 1, while flag 2, right? So these parts are not, you say, you check, these are not done, uh, these are not atomic, non-atomic. This is atomic critical section. So it it could be the case that either both of them are not true at the same time. So when it has gone inside, it may be possible that it checks that. So this is, sorry, P2 and F1. So it may be possible that let's say P1 is executing it. Okay, let's say P1 is executing it and P2 has not been executed. So flag 2 in this case will be false. So it will come inside the critical section, right? It will be operating in the critical section. Now in, let's say now, so this becomes false, it has come into the critical section. Now this one is true. Now let's say P2 has arrived. P2 takes its flag to true. Now it is taking the flag of 1. Flag of 1 is true. So it will wait in a busy wait, right? So when it falls, so after the critical section it turns flag 2 is equals to false, flag 1 equals to false, then only this will become false and it will enter the critical section. So obviously your mutual exclusion is satisfied, right? Only one at a time is able to enter it. So initially P1 was executing it, so at that time P2 was not able to execute it because flag 1 was false. So obviously your mutual exclusion was obviously satisfied. So mutual exclusion will be satisfied. Progress will also be satisfied because you see, uh, so you see one gets out, another comes in. So progress is always there. When none of them is inside, one will always get inside. Progress will also be satisfied. But the key thing is this bounded wait. Bounded wait will not be satisfied because this entire turn provides the bounded wait. It makes sure that after P1, P2 is executed, or if there are more than two processes, after P2, P3 will be executed like this. So this turn signal actually provides you this part that okay, now it is my turn, now it is his turn, now it is her turn, that kind of thing. So bounded wait is the one that is not satisfied. So bounded will be the correct answer. Okay, so let's come to the next one. Which of the following is incorrect? Counting semaphore can take integer values ranging over an unrestricted domain. This one is true. Binary semaphore 0 and 1, true. Binary semaphore can be implemented as a counting semaphore, true. Binary semaphore can also be executed as a implemented as a counting semaphore. The binary semaphore are same, be it 0 1 or counting. So none of this. Okay. So next one, in bounded waiting mutual exclusion solution using test and set operation for a system with n processes, the maximum number of time any other process may enter into the critical section after a process has been desired to do so is, so if you go into this one, if you go into this, you see the this is implementing a circular loop, j is equal to j plus 1 and all for waiting. So in a circular loop, what will happen? Length of the circular loop will be n minus 1, right? So except the one element. So if the length is n, so it is revolving n minus 1 time. So it has to wait at max. So if you have a list like this, so it swaps like this, and it checks which one is next ready to go. So at max, for a system with n processes, maximum number of time other processes may enter into the critical section after a process has desired to do so is basically n minus 1. At one time it has to enter. So match the columns. So deadlock, starvation, priority inversion. Deadlock, so this is a process may never be removed from the semaphore queue in which it is suspended. Number one is a process may never be removed from the semaphore queue in which it is suspended. That is starvation. two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting process.
Okay.
This is deadlock. Two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. Okay, and this is priority inversion because scheduling problem when a low priority holds a lock to a high priority problem. For a producer consumer problem with unbounded buffer size, semaphores needed are this is a very interesting question. You have a unbounded buffer. So how many semaphores are required? So one semaphore you require is correct, right? Mutex. Mutex lock you require. What is the other semaphore you require? So you used to have full and empty. Full value was 0 and empty value was n initially. Which one do you require? Empty was required to check overflow, full was required to check underflow. So if you have an unbounded buffer, overflow cannot happen, right? In an unbounded buffer, overflow cannot happen. Underflow can happen, right? So you require this mutex and the full. So the correct answer will be B, mutex. One thing I hope by far you have noticed like now, binary semaphore, mutex, and you have counting semaphore for atomic operation of update on variables. So these two are your your main keys that you need to remember. A binary semaphore is basically used here for a mutex locking. Counting semaphore is basically for atomic operation for update of your uh, variables. So this is the main logic. So in a bounded buffer producer consumer problem, suppose in the consumer process the wait statement corresponding to the semaphore full and mutex are interchanged, the resulting algorithm. So it is saying in the consumer process you have interchanged these two. You have interchanged these two. Will there be any problem? Obviously there will be problem because full checks for underflow, right? And mutex is log. So you are acquiring the log, but your buffer is empty, right? You have acquired the log and your buffer is empty. So that may lead to your deadlock, right? Because you have acquired the log and now you are saying your buffer is empty. Now you go and wait on that buffer empty statement, and as well as now neither any other producer can come and acquire the log to insert something into the buffer. So that will create a problem when the buffer is empty. So that will lead to a deadlock. Next is that suppose you have the following two codes. So the process P1 and P2. So what does this violate? So as we discussed that when we interchange these two, this basically cause in a deadlock where P1 waits for S2 and P2 waits for S1. So select the incorrect option. A process must execute wait mutex before entering the monitor and signal mutex after leaving the monitor. True. The signaling process can use next to suspend themselves. True, it uses the next for to suspend themselves. An integer next count is provided to count the number of processes suspending on the next. True. So there is nothing incorrect. All are correct. In Peterson's algorithm, if flag variable is not present, the resulting solution will violate what? So again let's come to here. So now they are saying
Yes.
yeah. So now they are saying that flag is not there. You have this variable. Uh, we have already found out this maintains your bounded weight, right? So what will happen if this happens? So if P1 is there, P1 will make while turn is equals to J, and P2 will do while turn is equals to I, right? And here the turn value is J, here the turn value is I. So basically both will just, so even if the critical section is empty, both will go into this infinite loop such that none of them goes inside. So it will cause the problem to your progress. So the correct answer is your progress. The mutual exclusion is happening, bounded weight is happening, but progress will be violated. So at the end of the day, flag ensures progress, turn ensures bounded weight, right? So with that we come to today's end. So thank you for joining. Next week we will again meet this time.
Thank you, sir.
Yeah.